Yeah. Welcome everyone. So for the preseminar and Discrete seminar, we have Matias von Bell, who is a graduate student at the University of Kentucky working with Martha Yip, and is going to talk about a unifying framework for the nu-Tamari lattice and principal order ideals in Young's lattice. So take it away, Matias.
Thank you very much, Alejandro, and thank you also for having me. Yeah, so I'll be talking about a unifying framework for the nu-Tamari lattice and principal order ideals in Young's lattice. And this is joint work with Rafael Gonzalez de Leon and Francisco Mayorga Cetina and my advisor, Martha Yip. And so for this pre-seminar portion, I thought we would go over some of the definitions and some notions that will be useful for understanding the talk. So I haven't done a pre-seminar like this before, and I think it's a brilliant idea. So we'll get to play around with some of the things that show up before the seminar. And then the seminar itself will introduce some things like the numerical flow polytope and talk about two different triangulations and talk about the dual graphs of those triangulations, and then some corollaries and connections to other work. But for pre-seminar, you can let me know if I'm not being specific enough or being too pedantic in terms of detail. I'm not sure how exactly, how formal or informal we should be in the pre-seminar, but I'm erring on the side of informal, so I hope that's okay. All right, so polytope P is a convex hull of a finite set of lattice points. So this is probably a definition that most of us are familiar with. And so if I take some lattice points in Rn, and then I take their convex hulls, so the smallest set of the smallest convex set containing those points, or and then fill out the interior. You can think of it intuitively as saran wrapping a set of points, and the shape that you roughly get is a lattice polytope, as long as we're dealing with lattice points as the vertices. And so one thing we want to do with polytopes often is triangulate them, and the way a triangulation is defined is that it's a collection of full dimensional simplices that when you put them all together, you get the polytope itself. And then any two simplices that you have, they intersect at a common face. And that common face could be the empty face, so they don't actually have to intersect. But if we have these two properties, we can call it a triangulation. And with a triangulation, an important notion that we'll see today is the dual graph of a triangulation. And that's a graph that's constructed by taking the full dimensional simplices in the triangulation and then drawing edges between any of the adjacent simplices. So if I have a two-dimensional picture here, something like this, and perhaps this is my polytope and my triangulated polytope, then I can take all of the full dimensional simplices, which in this case correspond to the faces here, and draw an edge between any two of them that share a codimension one face. And so then the dual graph is in the orange here. And this differs slightly from the graph theory notion of dual graph, where you also include the unbounded face on the outside. But and I think in graph theory, it might be called a truncated dual or something along those lines. But for us, we ignore the outside unbounded face. And for every simplex, we have a vertex, and every pair of adjacent simplices has an edge. Okay. And then we have this definition of volume for a d-dimensional polytope. And I'm going to use the word volume to describe the normalized volume. And that's going to be the standard Euclidean volume times d factorial. In particular, maybe I should draw something here.
So Matias, so I have a question. In the previous case, so the for if you have another triangulation, so I guess, yeah, the graph would be different.
Yes, exactly. Yes. So let's do a different triangulation. If my polytope consists of those points. So I had a point in the middle here, and so my polytope is technically, I guess, the convex hull of these sets, and I happen to have a lattice point inside. Let's do a different triangulation. Let's do something like this, like a star shape. Then in this case, my dual graph would look like a, what is that, a hexagon. So that's a good observation to make, that well, not every triangulation will give you a different dual graph structure, but different triangulations can give you different dual structures, dual graphs. So that's an excellent question, thank you. And then something about this volume here is that if we have a, for example, a unit square, Euclidean volume is of course 1, but then the normalized volume of this thing is 2, and that's because it's a 2-dimensional object, and so we multiply the Euclidean volume by 2 factorial. And one way to think about this is that if we have a unimodular triangulation of this polytope, meaning that every simplex has volume 1, then we can compute the volume by adding up the number of these simplices. And one more notion that's going to be important for us is the notion of integral equivalence between polytopes. So a lot of the polytopes we'll see today kind of live in ambient spaces that are, they might have different intrinsic dimensions than the dimension of the space that they're living in. And so we want to compare those polytopes and see if they're the same, even though they're living in perhaps different ambient spaces. And so one way to check that is using this notion of integral equivalence. And integral equivalence between two integral polytopes, that's an affine transformation from Rm to Rn. If P lives in Rm and Q lives in Rn, that takes P to Q. And so that phi is a bijection between the lattice, that's the Zm, the integer lattice, intersected with the affine span of the polytope P. And then, so it's a bijection between this intersection with the affine span and the lattice points in Zm, and also the intersection of the affine span of the polytope Q with Zn. So perhaps we should do a little example of this one to help know what this means. So a simple example would be the following. Let's draw some lattice points in here. Okay, and suppose I have a little polytope that's just a line segment here between these points. And I might have a different polytope. Let's call this one P. And then I have a different one down here, say, like this. Call this one Q. And so we want to see if these are integrally equivalent. And the integral equivalence in this case is actually just a projection down from R2 to R. So the integral equivalence here would be R2 to R, and it's going to just be taking xy to x. And let's look at the affine span of this polytope P. So that's going to give us the line here, y equals x, and its intersection with lattice points will then be these sets of lattice points along that line. And we can see that under this projection, those lattice points go exactly to the lattice points, or well, to the integers on on the x-axis. So these are, even though these live in different dimensions, technically these polytopes, this one might live in just R, this one lives in R2, but they are still equivalent. And one thing that's important about this integral equivalence is not only that you get combinatorially equivalent polytopes, so their facial structures and everything are the same, etc., but it also preserves the volume. And if you know what the Ehrhart polynomial is, then it also preserves the Ehrhart polynomial. So it's a useful transformation that preserves the normalized volume or volume of the polytope. Okay.
So for example, in this case, the volume would be, the normalized volume would be
1. Right, yeah, good. So here, in this case, the volume would be just the length. Right, okay. So these are some geometric notions that will be going on in the background, but let's talk about some combinatorial structures as well. So we got nu-dict paths. These are things that will show up. So you might have heard of dict paths before. They are very common combinatorial objects. So this is a particular generalization of them. So we start with a path called nu here from the origin all the way to some endpoint BA. In this case, that is 5, 3. And then a nu-dict path is a path that stays weakly above the path nu that we chose. And so a path nu then defines a collection of nu-dict paths. So something like this would not be allowed because that stays, or that crosses over nu, the shaded region. And so then a valley is going to be a consecutive east-north pair, and a peak is a consecutive northeast pair. And this is for reasons that are obvious if you tilt your head 45 degrees to the left. So you get a valley here and a peak, for example, here. And so just to point out the generalization here, that when nu is a staircase lattice path in a square kind of grid like this, then you obtain the classical dict paths that stay weakly above this. And we can then define the nu Catalan number to be the number of nu-dict paths, just like the classical Catalan numbers count the classical dict paths. And so Catalan numbers are a fun sequence of numbers, starting something like this. The next one's 14, and so on. And the general formula is 1 over n plus 1 to n choose n. But in general, for there's not a closed form positive formula for the number of nu-dict paths that is known as far as I'm aware. But there is a determinantal formula that will make a little bit of an appearance today in the talk, but I'll save that for then. And so one of the lattice structures we can put on these nu-dict paths is Young's lattice. Well, actually, I should rephrase that. It's principal order ideals in Young's lattice. So briefly mention now what Young's lattice is. It's the lattice on integer partitions ordered by inclusion of Young diagrams. So it looks something like this, where integer partitions, if we look, for example, at the row 4 here going upward, or rank 4, then these are all the ways to partition the number 4, the integer 4. So this is the partition corresponding to 4, and this is 3 plus 1, this is 2 plus 2, 2 plus 1 plus 1, 1 plus 1 plus 1 plus 1. And so those are all the integer partitions. And then this is the partially ordered set here is ordered according to inclusion on these Young diagrams. So for example, this one is included inside of this one, so it's below it. And so what we're going to be thinking about today is our principal order ideals in this Young's lattice. And we can denote a principal order ideal by I nu, where for our lattice path nu, if you look at this lattice path nu here, and look at just the region here above the path, then that looks exactly like a integer partition here. So there's a natural correspondence between these partitions and nudec paths. And so a principal order ideal is then all of the all of the integer partitions that are below the one that generates it. So it's principal because it's generated by a single integer partition here. So everything in the downset of this partition is included, and that forms a lattice structure that is, a lattice structure within Young's lattice. Okay, and the cover relation here is pretty straightforward. You can go up along this lattice if you take a peak and then you bump down a peak into be a valley instead. So this one has two peaks, so you can either push this peak down and go up, push the top peak down and go up this way, or you can push this peak down and go up the other way. So that's pretty straightforward. But there is another lattice structure as well on nudec paths that's given by, or that's called the nu-Tamari lattice. And to show you what that looks like, we need to first define a horizontal distance on points on a nudec path and define an operation that's perhaps less well known. So the horizontal distance of a point P is the number of e-steps that can be taken from P without crossing nu. So quiz time. What would be the horizontal distance of this point R? Anyone can feel free to type it in the chat or say it out loud. Any brave souls out there? Okay, let me see them. Someone's in the chat. Yes, it's 2, exactly. Right, because you can take 2 steps here from 2 e-steps, but then if we took a third one, we would go into the shaded region, and that's not allowed. We would be crossing nu. So this horizontal distance is 2. Is there a question? Yeah, cool, awesome. And so this one's 2, but if we had a point here, P down here, this one would be 0 because we can't take a single step. And then using this notion of horizontal distance, we can define a rotation of at a point P by switching the e-step preceding this point P with the subpath from P to another point Q, such that the horizontal distances are the same. So let me give you an example of that to kind of see what's going on. So here's my point P, and the horizontal distance is 0. The next point has horizontal distance 2, then 1. And then on the top here, we have 3, 2, 1, and 0. And so the next point along this path that has the horizontal distance the same as P is Q over here. And so what this rotation does then is it takes the e-step preceding the point P and puts it at the end of this, this subpath in between here. And so this is called a rotation on a nudec path. And this rotation then induces a cover relation. We obtain one path from another by rotation. Yeah, go ahead.
Oh, geez. So, Matias, could you maybe show the cover relation again? Thank you, sorry.
Yeah.
Sorry.
The cover relation is up here, or did you want the picture? Okay. Yeah, so define the cover relation. One path is covered by another one if the other one is obtained from pi1 by a rotation. And so the nu-Tamari lattice is the lattice on nudec paths induced by the transitive closure of this cover relation. And so meaning that if path A is covered by path B and path B is covered by path C, then A is less than C in the lattice. So here are 2 examples. The classical one is on the left. It looks like this. But then the generalized one in this case for this particular path nu is on the right. So this is the nu-Tamari lattice for the lattice path nu on the bottom that's circled.
And yeah. Could you maybe put the picture again of the rotation?
Yeah,
thank you.
Right, so the path, sorry, the E step here at the beginning of before P, that gets rotated to the end, and everything in between the subpath gets shifted 1 unit to the left. And the important thing is that you always pick the next point along the path that has the same horizontal distance. There might be multiple ones, but you have to pick the first one. Okay, so this is
Is it possible that after a rotation you get the same path?
No, okay. I guess I forgot to say one thing that you can, or did I mention it here? It's not possible because I actually forgot to mention here, so that's a good clarification, is that the points that you look at have to be valley points. And so for example here, you can only consider these rotations for every valley. So the only possible places I could define a rotation here are those 2 points. And so technically, or because that restricts us so much, we can't rotate to the same path from itself. But that was a very good question. That was my bad. I forgot to specify that P has to be a valley point. Thanks for that. And yeah, so looks like oh, that's awesome. So Vertel is my uncle's nephew. Yeah, so yeah, I forgot to mention that this description of the nu-Tamari lattice is introduced by Vertel and Viennot. All right, and we'll see another version of this during the talk. But some other quick things I wanted to say was just, I'm sure many of you, if you've seen Alejandro speak, I'm sure he's spoken here before, probably has spoken about flow polytopes, but I just wanted to quickly define that as well, because they will make an appearance so we can make sure that we understand them for the talk. So a flow graph G is a connected directed graph on a vertex set 1 through n, and everything, all the edges are directed from smaller to larger vertices. And then we're going to define a flow of size 1 to be a tuple on x sub e, where e is an edge in this graph. And it's going to be a tuple of non-negative real numbers, so that flow is preserved at every single vertex. And so in the vertices here, 2, 3, 4, the inflow has to be equal to the outflow. And so that's captured by this equation here. And then also, in addition, this is a flow of size 1, so the inflow at the source of this graph here in the beginning has to be 1. And then the outflow at the sink has to be 1 as well. So let's do a little example here. If I give these flows here 1/2, 1/3, 1/6. So that should add up to 1. So there's 1 flow coming in here. And then at the vertex 2, there's only 1 other option for flow to be preserved. So we keep giving, or we keep 1/6 flow on this edge. And then at vertex 3, we have 2 incoming flows, 1/3 and 1/6. So those add up to 1/2. So now we have 1/2 flow that can be split up among these 2 edges here. So I'll split them up as 1/2 and 1/2. Oh, whoops. I'm breaking the rules here. 1/4 and 1/4 would be better. And then at the end here, I have incoming at vertex 4. I have 1/4 and 1/2, so that is 3/4. And now the outflow is 1. So this is one particular flow of size 1. If we consider all of the sets of possible flows of size 1 on this graph, then we obtain what's called the flow polytope. So it's the set of all possible flows of size 1 on the graph G. And it's going to be a polytope in dimension. It's living in dimension r to the m, where m is the number of edges in the graph. and this is known as the flow polytope. But the actual inherent dimension of the polytope itself is has an interesting formula. It's dependent entirely on the number of edges and vertices in the graph. So the dimension of the flow polytope is the number of edges in the graph minus the number of vertices in the graph plus 1. Okay.
Matias, would this be a good time to stop for?
Sure. This is a great time. I was just gonna show an example to leave you to think about what's the flow polytope over this little fun graph here.
Great. So let's thank Matias for the preseminar. So you can put your reactions or in the chat. Are there any questions to Matias? So I have a question about the so you mentioned that the volume, you count the number of simplices. So that's, so in terms of this dual of the graph, that's like it would be so that would be the number of vertices of the volume would be the number of vertices of that.
Yes, exactly. Right. And so we can see that if we go back, for example, here in either of these dual structures. So we'll get one simplex for every single nu-dic path here. And so the volume is counted by the number of these vertices in the graph. And so this graph itself here actually has the additional structure of being a lattice, or the Hasse diagram of a lattice, if we think about it that way. But yes, the number of vertices in the graph correspond to the volume in the triangulations that we'll be talking about.
For the new Catalan numbers, so you said there's no closed form, but are there any other particular news besides the staircase that do have some nice form?
Yeah, so there's, I don't remember the formulas off the top of my head, but the rational cases do have a formula. So a rational case, I mean, if I have a grid like this, where these are co-prime, so it's a path from the origin to co-prime integers, a lattice point where these 2 points are co-prime. So we saw 3 and 5. So in that case, there is a formula, and the formula is, so the path nu is determined by the line here going diagonally across. So we shade in all the boxes that touch that line like this, and that determines a nu. And then once we do that, then there is a formula for the rational case. Yeah, that's a good question.
Okay, so we can maybe take